Difference between real and virtual images. 1. A real image can be formed on the screen. A virtual image cannot be formed on the screen. For real images, the light ray will actually meet at a point called the principal focus. For virtual images, the light rays do not meet to form a real image. They actually meet to form virtual image. They appear to diverge from the principal focus. Real images are generally inverted, while virtual images are generally erect or upright. 4. Real image is always on the same side as object for a mirror. That is, the real image is always in front of the mirror, but on the other side for a lens. For a virtual image, the image is always on the other side of the mirror, that is behind the mirror, but on the same side for a lens. We can reach to a real image, but for a virtual image, we cannot reach to it. What it means is that we can actually see the images formed on the screen for a real image, while for a virtual image, you just see the images behind the screen where you cannot actually touch it. Then we look at examples of real image. Examples include images formed on cinema screens, images formed on the retina of the eye, and the images formed on the films of cameras. For a virtual image, examples are the images you see in a plane mirror and convex mirror. In fact, a man standing in front of a plane mirror sees the image of himself inside that mirror. That image that he sees is a virtual image. Apart from plane mirrors, curved mirrors also reflect light incident on them. In this video, we shall consider only those curved mirrors which form part of the surface of spheres. Such mirrors are therefore called spherical mirrors, and they have a large number of scientific and practical applications. For example, shading mirrors, car driving mirrors, parabolic mirrors of telescopes, mirror reflectors of searchlight are such applications of this mirror. There are two types of curved mirror, namely convex and concave mirror. So this is a convex mirror. The inner side, the inner part of the mirror is silvered. That makes it a convex mirror, and this other side represents the reflecting surface. For this, the outer part is silvered, as it can be seen from this shaded part, while the inner side is left on silver. So the inner side is the reflecting surface of the concave mirror, while for this, the outer part is the reflecting surface of the concave mirror. So these mirrors are made by silvering the glass surface, which is a part of the sphere. If the inside surface of this spherical part is silvered, and the outside surface is the reflecting part, the resulting mirror is called a convex or diverging mirror. So as you can see from here, this is the convex or the diverging mirror, because the inside part is silvered while the reflecting surface is the outer part. If the outside surface is silvered, now you can see this, the outside surface is silvered and the inside surface is reflecting part, this side, then the resulting mirror is known as a concave or a converging mirror. So this is a converging mirror or a concave mirror, while this is a convex or diverging mirror. So let's take a look at the essential parts of a spherical mirror. So the first part, we're going to look at the aperture. The aperture is the width AB of the mirror. So let me quickly show you that. So on these diagrams, the opening here, this opening here, AB, is known as the aperture of the converging mirror, while the opening here also, AB, is the aperture for a convex mirror. The pole, P, of the mirror is the center of the reflecting surface. Then let's look at 3. The center of curvature, C, is the center of the sphere of which the mirror is part of. Also, we can differentiate between the pole P of the mirror and the center of curvature of the mirror. The pole P of the mirror is the midpoint on the reflecting surface of this mirror. That's the midpoint between the arc AB, and also for this, the midpoint between the arc AB. Now, C, the center of curvature, is the center of the sphere from which the mirror is cut from. Let's take a look at this. Let's assume that I have this as a sphere. This is my sphere. The midpoint of this sphere here, at this point here, gives the center of curvature of that sphere. So if I cut any part of this, let's say for example I cut off this part this way and I move it this way, then this part here is going to be the center of curvature of my mirror. So just so you can see this, even though when I take off this part, you see that this is now my mirror. The center of this point here will be the center of curvature of this mirror, but the midpoint gives me the pole here. The midpoint of this gives me the pole P of the mirror. So you can differentiate between the pole of the mirror and the center of curvature. See, the center of curvature is actually the center of the sphere, while the pole is the midpoint on the circumference of the mirror. Let us look at the radius of curvature R. The radius of curvature is the distance CP. It is the radius of the sphere of which the mirror is part of. Then again, we can look at the principal axis. The principal axis is the line PC from the... Okay, this line that starts from C to P represents the principal axis. While the length of the line, you can see here the length of the line is the radius of curvature. The radius of curvature is measured from the center of curvature of the mirror from the pole of the mirror. So the distance from C to P gives the radius of curvature, while the line that joins C to P refers to the principal axis. Next, we are going to look at the principal focus. Here I'm going to divide the principal focus into two parts. Here we have the principal focus for a converging mirror, which is a concave mirror, and we also have the principal focus for a diverging mirror, which is the convex mirror. So for a converging mirror, the principal focus F of a converging mirror is a point on the principal axis to which incident rays, which are parallel and close to the principal axis, converge after reflection. then for that of a converging mirror, the principal focus is a point on the principal axis to which incident rays parallel and close to the principal axis appear. They will appear to diverge after reflection. So when they will appear to diverge after reflection. So at that point where they appear to diverge after reflection is known as the principal axis. Now this is what I want you to understand. For the principal focus, this is the principal focus of a converging lens, this point here F. It is the point where any ray that is parallel. Let's say for example, if I draw a rail parallel and close to the principal, this is my principal axis here. If I draw a line parallel to it like this, so this is an incident ray. So a ray that is coming from here that is incident on the surface of the mirror will tend to be reflected through F here. This is F. So all the ray will come back from here and be reflected through this point, which is the point of what? F. This is the reflected ray. But for a diverging mirror, the rays will not actually converge here. Any ray that is parallel to this is an incident ray that is parallel to the principal axis and close to it. This is what is going to happen. It is going to appear as if the rays are coming from here. Now the rays will appear to come from this point here. You can see that the rays are appearing to come from here. So I'm going to break the lines, showing that the rays are not real rays. The rays do not actually intercept, but they appear to come from this place when you look through the mirror. So you can see that the ray here coming this way, when it touches the mirror, from the mirror, when you look through the mirror, the rays will appear to come from this point here. So this is a diverging lens. So the principal focus do not actually, the convex mirror do not actually focus convert the images or the rays at F, but rather they diverge them, they make them to appear as if they come from F. But for this, the ray will actually converge at F. They will meet at F. They will always pass through what? F. All the rays will come and meet at point what? F. Formation of images by curved mirrors. There are 4 rules that we use to combine curved mirrors. Let us take a look at these 4 rules. The first rule is that a ray close and parallel to the principal axis is reflected through the principal focus. So this is my mirror, the principal axis CP. So if I draw a ray or an incident ray that is parallel to the principal axis CP, the ray will be reflected after striking the curved mirror through point F. That is the principal focus of that mirror. Rule number 2, a ray passing through the principal focus is reflected parallel to the principal axis. So let's take a look at this again. So when I draw a ray through the principal focus F, I will always indicate my directions to show that this is an incident ray. So the direction points towards the mirror. The ray will be reflected from the mirror parallel to the principal axis. So get a parallel ray to CP. Again, I will indicate my direction pointing outward from the mirror. 3, an incident ray passing through C, the center of curvature, is reflected back through C, which is the center of curvature. Now, if I draw a ray through C and it strikes the curved mirror at the surface of the curved mirror, let me indicate my directions, showing that it is the incident ray pointing towards the curved mirror. The ray will be reflected back through C. So the green ray represents the reflected ray, and the arrows are included to show that the rays are pointing out from the mirror. 4, an incident ray that strikes the mirror at the pole P at an angle is reflected back through the same angle on the other side of the principal axis. So let's take a look at this. So when I draw a ray that strikes the plane mirror at P at an angle, so I'll draw a red line to represent that angle. So this, the red angle here, the ray will also be reflected back from the other side of the principal axis CP at the same angle. So I indicate the directions. So here is the reflected ray at an angle which is equal to the red angle. So I'll draw that with a green line. So these 2 angles are equal to each other. So this is my reflected ray. I have to indicate the direction of the reflected ray. So a combination of any 2 of the above gives the position, nature, and size of the images formed by the curved or spherical mirror. Okay, now let us look at the nature and the types of image formed by concave mirrors. The nature and position of images of the image formed by a concave mirror depends on the position of the object in front of the mirror. Now there are 5 possible positions that the object can be. The object O can be beyond C. This is center of curvature, beyond the center of curvature, between the center of curvature and the principal focus F, and also at the point F at the principal focus. The object can also be at the point between the principal focus and the pole of the mirror. So the object can be beyond C, it can be at C, it can be between C and F, it can also be at F, and it can also be between F and P. And at these various distances from the pole of the mirror, the images formed are different. So we're going to take a look at that and see how the images are affected by these positions. So the first part is object beyond C. So I'm going to draw an object that is beyond C. So if I place an object here beyond C, I need to indicate the direction. The direction of the object must always be upright, or you can do it inverted and you get an upright image, because the image is going to always be inverted. Now let's draw a ray that is incident from the tip of this. Draw a ray that is parallel. Remember our combination of rules for drawing rays of light. So a ray that is parallel to the principal axis will be reflected back through the principal focus. So this ray will be reflected through the principal focus here. So I'll indicate with my arrow. Remember that a combination, any 2 combination will give me the value of my image, where the image will be formed. So I'll get another image, another ray, incident ray. This time around, I'll take the incident ray through F. So when it passes through F and strikes the mirror, let me indicate my direction. It will be reflected parallel to the principal axis this time around. So I'm going to have a ray that is reflected through this. So I'm going to indicate my directions again to show that this is a reflected ray. Now you see the image will be formed at this point here. The point of intersection, this is where the image will be formed. So I'll draw a straight line from the principal axis down to this point. Okay, I'll draw it from this point this way. Then I'm going to indicate with arrows here that the image is inverted. Now this is the image formed. Now I'm going to look at the nature of the image that is formed. The nature of the image that is formed is that the image is real, inverted, diminished, and formed between C and F. So this image is smaller than this. It is real. You can see with the arrow that it is upside down, so it is inverted. Next, object placed at C. So the object is placed here. So let me draw the object at C. So this is my object at C. So I'll indicate with my arrows the directions. So I have to draw a ray from the tip parallel to this, to the principal, to CP, the principal axis. Indicate my direction. So the ray will be reflected through F because it is parallel to the principal axis. So I indicate my direction once again. Then I have to do another combination of a ray. So I take a ray passing through F, and this is an incident ray passing through F. That ray will be reflected parallel to the principal axis. So as you can see there, the green colored reflected ray drawn parallel to CP. So I have to indicate my direction once again. So this is my direction. Now you can look at the point where the rays intersect, the green rays intersect. They intersect immediately below C. So I'll draw my image there. So representing the black lines, or the dark lines rather. So I indicate my direction and to show that the image is inverted. So the image is of the same size as the object. The object and the image are of the same size, and it is real, inverted, and formed at C. So you can see the nature of the image here. The image is real, inverted, the same size as the object, and formed at C. So this is the nature of the image that is formed by an object that is placed at C. Next, object placed between C and F. So I'm going to draw my object and place it between C and F, anywhere between C and F. Indicate with my arrows the direction of the object. So a rail that is parallel to the principal axis will be reflected through F. So I need to indicate my directions. And a ray that is incident on the mirror through F will be reflected parallel to the principal axis. So their point of intersection shows where the image will be formed. So I'm going to indicate with my arrows vertically downward. Here, the nature of the image form is that the image is real, inverted, magnified, and formed beyond C. You can see from here that the image is actually formed beyond C. The image is larger than the object. It is also real, and it is inverted. Next, object placed at F. So if I place my object at F, indicate with my arrows, I'll draw a rail parallel to the principal axis. A ray parallel to the principal axis will always be reflected through F. So this is my reflected ray through F. So I indicate with my arrows the direction of the rays. Now I'll take another ray. This time around, because this object is placed at F, I can't draw rays through F. Incident ray. So I'm going to draw an incident ray through C. So an incident ray through C from the tip of this. So I indicate with my arrows the direction of the incident ray. As it strikes the mirror, what happens is that it will be reflected back through C. Remember that? So when it is reflected back through C, I'll take my directions this way. Now you can see from here that these rays can never intercept each other. Since the rays can never intercept each other, we say that the image is real, inverted, magnified, and formed at infinity. So because the image is so large, it will be formed at infinity. The image will not be formed at near point. It will be formed at infinity, very far, very large. The image is very large. So the image is formed at infinity. So this is the image formed when the object is placed at, this is the nature of the image formed when the object is placed at F. Next, object placed between F and P. The object placed between F and P. So when the object is placed between F and P, this is what we're going to get. I'm going to place the object here, and I will indicate with my directions. Okay, let me move this a little bit this way, and then I will extend this to this other point. So when the object is placed there, so we take incident ray, an incident ray that is parallel to this, to the principal axis, okay, with my direction, will be reflected through F. Now these rays will extend backward, because this time around, the rays will appear to be coming from F rather than actually coming from F. So the rays will actually be broken because they are not real. They are not real rays, intercepting rays. So they appear to come from this point here, F here. So indicate with my direction. So this reflected ray are actually going up this way. Okay, this way. Now this time around, they appear to come from this position like this. Then we know that another ray that passes through C from the tip will go up this way until it intercepts with this ray on this side. So the direction of this ray is going to be this way and also in this way, because it is back and forth. So the image will be formed here at this point of intersection here, and the image is going to be erect and virtual. So I'm going to break the lines to show that they are virtual images. So the images formed are virtual images. So that is why I am breaking the lines. So the nature of the image formed here is that the image is virtual, it is erect, and it is also magnified. You can see that the size of this image here is greater than the size of the object. And this is the only case where the image is formed behind a concave mirror. So for all other cases, the images are always formed in front of the concave mirror. But when the object is placed between F and P, the image is formed behind a concave mirror, and it is virtual and also erect. Now, images formed by convex mirror. The images formed by convex mirrors are always virtual, diminished, erect, and formed behind the mirror. So let's take a look at this. Now, look at this. The focal length or the principal focus of a convex mirror is actually behind the mirror and the center of curvature too, because you know that it is the inside of the mirror that is silvered for a convex mirror. So let me draw an image anywhere, irrespective of the position of the image, of the object rather. The image form is always diminished. So I have an object drawn here. So my object is placed in front of the mirror. Then I'll use a ray of light. Okay, let me indicate my direction. You always have to indicate your direction. It's very necessary. So a ray of light that is parallel to the principal axis. Now, instead of the ray of light to converge at F, the ray of light will appear to be coming from F. So it will appear to come from F this way and go up this way. Now the rays are not real rays, so I'm going to break those rays to show that they are virtual rays. The rays are not actually coming from there, but they will appear to come from this point. And finally, I can just get a ray of light that passes through C. So for this, we already know what will happen. The ray will be going this way. So that's the incident ray. The incident ray will go this way, and the reflected ray will also go back this way. So the point of intersection here, you can see where these two lines intersect is this point. So that is where the image is formed. It is erect, it is virtual. So I'm going to break the lines, and it is diminished. So this is the image, simple image formed by a convex mirror. For a convex mirror, irrespective of where you place the object, the image must always be formed inside the mirror, behind the mirror. It must be erect, it must be diminished.